Okay, good morning, everyone. It's 9:45 and I want to talk to you a little bit and then we're going to do a lab. Okay, so this is a very simple lab that you would be doing in class if you were with me. Here I have a simple setup. This is a rubber pipette that has blue water in the bulb. And I trapped air in the stem of it using this thing, which is called a Hoffman's clamp. It clamps down on the end and squeezes it tight so that no air can leak. Hopefully, that's the idea. So there we go, that's our setup. Then you'll see Charles' law. Charles' law, notice, is temperature and volume relationships.
Okay.
So I have a set of 5 beakers. Here's the first one. Notice it has ice in it. And here is a syringe. I've trapped air in here. There's 5 milliliters of air. Looking to see if I put this in here in the cold ice water, what happens to the volume, right? And what would be the prediction? Somebody answer.
It would shrink.
It would go down.
Yeah, it would shrink or go down. So we're compressing it by putting it in here. So I'm gonna put it in here. We're gonna let it set while we do the other lab so it can get to equilibrium with the water. Okay, the next one. So it is like cooler tap water. So there we go. Same thing, putting that in there. So here's my hot tap water. So I'm gonna put this, also set it up so that it can come to equilibrium. This one is 5, and I'm using my tea kettle to put what was once boiling water in it. And again, a 5 milliliter syringe of air, and I'll stick it in there to come to equilibrium setup. So there it is. We have all 5 beakers with syringes in them. We're gonna let them set for 10 minutes or so, or however long it takes us to get through the other lab. Now this is an example of what law. Somebody unmute themselves and answer.
Boyle's law.
Boyle's law is correct, which is what? Whoever answered.
No, that's still me. V1 equals P2V2.
Right, it's volume and pressure relationship, right? Generally speaking. So volume is going to be measured in here with the stem. Pressure is going to be on this bulb right here. We're going to actually use chemistry books as our pressure units. So I'm going to set a book on it. It's obviously, you can predict what's going to happen. It's going to squeeze water into the stem, and we're going to measure the length. So here's our setup. We have an original, so this would be without any books causing pressure. So we have what, 8.2 millimeters. That's how it should look. So pressure, 1 book. So we're gonna put this on there. 6.2, we'll say, instead of 1.2. 6.2.
And 1 book.
That is 1 book. So just so. Okay, book number 2. So now we're at
5.1?
5.1 millimeters. Okay, book number 3. Now we're at about 4.3, we'll say. There we go.
What?
In book number 4.
Yeah,
What did I say?
5.
So sorry. 3.2, 3, 4. 3.4.
All right. Book number 5. $3.4. That's exactly what we got last time.
Yeah, it's not moving now.
Hmm.
Yeah, go ahead and do 3.4 again. We'll do our last book. And that could be
Like 3.1.
3.1.
That's book number 6.
So see, there's 6 books. Okay, so here it's obvious that the more books we have, the less volume we have. So it shows the Boyle's Law relationship. So now you are going to follow the instructions for rules for the graphs at the top and graphing the data at the bottom. You're going to make your own graph. So flip over to the back. Let's complete the second section. Okay,
So this is number
so we're
5.
actually going to go backwards.
This is a really hot one.
So this is the hot one that we did, and I'm going to push it a little bit and then let it release just so it doesn't get stuck. But here's the 5, and then if you count up, it's about 5.5. So 5.5 milliliters.
Is for number 5.
And this is for a temperature, so 71. Okay, so obviously we had a little expansion going on because of the hot water. Here's the second one. Again, I'm pushing on it only to release it from sticking.
This is number 4.
Mhm.
Yeah, hot tap.
So we'll see what temperature it is. So this one's 40 degrees Celsius, and it didn't change much. It's still at 5.
So 5 milliliters for number 4. There you go.
This one is the cooler tap water, but it doesn't have any ice in it. So there we go, 20.2 degrees Celsius. This one, so 17.7 degrees Celsius. And it didn't change.
This isn't working very well, is it?
Well, the extreme temperatures
Are going to be the ones.
are going to be the ones that are more visible. So this one's 4.1 degrees Celsius.
Very cold.
And
Much less.
4.9.
Got a little bit.
A little bit.
So it's more obvious on the hotter side.
Yeah, so extreme temperatures like the ice and the
Boiling.
boiling work better. It's not a perfect little lab.
Upside down.
Let me show you this instruction right here. So it says to extrapolate to a 0 volume. So here, I'll just do this one for you. So I have 4.1. These are marked for you. So it's, first of all, you have to figure out this is 10, 20, 30, 40, 50, 60, 70, 80, 90, 100. So each of these is 10. So your numbers are going to be
All right there.
all kind of in this area. So it's 4.1, so a little less than half of this line. And then 4.4 milliliters. So if this is, oops, sorry, 0, 1, 2, 3, 4, 5, and 6. So my data point is going to be here. So let's pretend these are our dots. And then you're going to extrapolate best fit line like that. The point here is, at what temperature is the volume of air at 0 milliliters? So you're looking for the x-intercept. It's right there. So it's negative 220, 1020. So your number is negative 220. The point here being that you're looking for absolute zero. What is absolute zero?
Negative 273.15.
Right. So we're off, but that's because our data is bad, right? We have technical difficulties, but that's the idea of this graph, is to extrapolate that number of 273, okay? So that's the point of this activity.